a random variable is said to be continuous if its cumulative distribution function is continuous and possibly differentiable in all but a finite number of points. The countable number of points. In that case, we define a PDF as the derivative of the CDF, the cumulative distribution function, where the derivative exists. And we can, set the PDF, the probability density function, to an arbitrary positive number otherwise. The point of the PDF is when we integrate it, it gives us a probability. So when we integrate the PDF probability density over a region of the real numbers B, you find the probability that the random variable x takes values in this region B. All right, so let's see some common examples. The simplest, I guess, example of a continuous distribution would be the uniform distribution. So if x is uniform between a to b, where a and b are real numbers, a is less than b, this means that the PDF of x is 1 over b minus a. So it's a constant PDF, flat, for values between a and b, and 0 otherwise. Okay. Another example that we will use a lot during our discussion of stochastic processes, especially the Poisson process, is the exponential distribution. So x is exponential with parameter lambda if the PDF of x is equal to lambda e to the minus lambda x whenever x is bigger or equal to 0. Now, consequently, if you integrate this, you can see that the complementary CDF, meaning the probability that x exceeds any value x, decays exponentially like e to the minus lambda x for positive values of x, of course. Now, if we plot this, we will see that, let me see. If we plot this, we will see that the complementary CDF decays exponentially. So the probability that x exceeds a value decays exponentially with the value, and the rate of this decrease, the slope of this decrease, is controlled by lambda. The larger the lambda, the faster the fall. So a consequence of this complementary CDF is the memorylessness property of the exponential random variable. Memorylessness property means the following. The probability that x exceeds a value t plus x, given that x is already larger than t, well, this is simple to do, really, because this is simply equal to the probability that x is larger than t plus x, and x is larger than t, but this is simply the same as x is larger than t plus x, divided by the probability that x is larger than t. And when you plug in the numbers, e to the minus t plus x divided by e to the minus t, you get e to the minus lambda x. So what does this mean? It says that even if we know that x is larger than t, this does not tell us anything about how much further x can go. It doesn't give us any information about how much further x is going to go. So in fact, this will mean more when we think of x as the inter-arrival time in a discrete stochastic process, namely the Poisson process. So this is known as, so basically if you were waiting for the bus and the inter-arrival times between buses are exponentially distributed, and you know the mean inter-arrival time is 10, but for some reason you started waiting, I don't know, 15 minutes ago, and there's no bus yet. The expected amount of time you will wait is still 10. The distribution of the extra amount of time you will wait is still exponential with rate 1/10, so it doesn't really matter. So that is the memorylessness of the exponential distribution. Another very important, by the way, the discrete correspondent of this distribution is the geometric. The geometric random variable also is memoryless. And that comes from the fact that the geometric is simply counting the number of trials until we get a success. But previous trials, the result of previous trials does not influence how many more trials we're going to do. I mean, how many failures we've had so far has no influence on when the first success is going to happen. So the geometric is the discrete counterpart of the exponential. Another very important random variable that we all know from a lot of engineering scenarios is the Gaussian. So if x is said to be distributed Gaussian, according to a Gaussian distribution, with mean, mu, and variance sigma squared, if the PDF, probability density function of x, is given by 1/2 pi sigma squared e to the minus x minus mu squared over 2 sigma squared. And that is for all real values of x. So when you plot this, it has the familiar bell-shaped curve. Suppose mu is somewhere here. Suppose it's positive. This is x. Mu is here. So as you can see from here, this is an even function centered at mu. It is evenly distributed around mu, and it decays as x minus mu grows. Okay, so it starts here and has decaying tails. So let me try to draw a resemblance to a Gaussian. It kind of looks bell-shaped, the bell curve that a lot of people are familiar with. Now, how fast this drops is controlled by this variance. The square root of this variance parameter is called the standard deviation. We'll formally define the concepts of variance and standard deviation later on, but this shape is controlled by sigma. How widespread or how concentrated it is around mu is controlled by sigma. And in fact, let's go, for example, to mu plus sigma and mu minus sigma around the center. Roughly 68% of the whole area of this curve is concentrated in this shaded region. Right. Now, we use the Gaussian a lot in modeling things in engineering. For example, noise processes are often modeled as Gaussian in electronic systems and in communication systems. And the Gaussian is used again wherever there are many independent similar disturbances adding together to form one disturbance. And this is a consequence of the central limit theorem, which we will talk about later. Now, when we use a Gaussian, as you can see, I did not explicitly identify a cumulative distribution function for it. The cumulative distribution function, obviously, you can get by integrating this, but it does not have a it does not have a known closed form integral. We often use the standard Gaussian. We say normal with mean 0 and variance 1. We call it the standard Gaussian. And the fact that we could perhaps prove later is that when you scale a Gaussian, it is still a Gaussian. So if x is normal with mean mu and variance sigma squared, if you were to scale x such that if you get a y, which is x minus mu over sigma, right, you can show that y is standard Gaussian. Because we took the mean out and we scaled by the standard deviation. We can show these things later. But you obtain a standard Gaussian this way, and we can use this in computations. The CDF of the standard Gaussian is usually denoted with this function phi, and it basically is the integral 1 over 2 pi integral minus infinity to infinity to x, because it's a CDF, e to the minus y squared over 2 dy. And if you were to integrate minus infinity to infinity, obviously you will find 1. Now this function, the Gaussian CDF, is symmetric around 0. Phi of x is the same as phi of minus x. And the symmetry comes in very handy in computations. Let's see, for example, a simple example. If we want to compute, let's say x is normal with mean 3 and variance 15. And we want to compute the probability that x is less than or equal to a for some a, so for some value a. What we can do is we can express this as the probability that x minus 3 over square root of 15 is less than or equal to a minus 3 over square root 15. Okay, and this is a glimpse of how we work, by the way, with a function of a random variable. And since this, by our normalization idea, this is normal, okay, let's call this y. This is normal with mean 0, variance 1. This is equal to phi of x minus 3 over 15. We'll do further computations with the Gaussian later on, and we will in fact also discuss Gaussian random processes in this course.